Hello everyone, my name is Jae-Yoon Kim. I'm a PhD student in Korea University under the guidance of Professor Kim. And today the topic of my presentation is fracture mechanics analysis of hydrogen embrittled API X52 steel pipe using small punch test data. As emerged as a renewable energy, the structural integrity of hydrogen pipeline has been investigated. However, in the case if the micro cracks occurs in the hydrogen pipe, the hydrogen atoms are concentrated and penetrated into the crack tips. Then the material properties such as ductility or fracture toughness could be degraded. Therefore, it is necessary to analyze hydrogen embrittlement effect on material properties for structural integrity of the hydrogen pipelines. For the crack stability assessment based on the fracture mechanics analysis, usually the stress intensity factor or J integral values for applied load is compared to the material properties such as fracture toughness. In our studies for the failure assessment of the cracked pipes, the failure assessment diagram, FAD, which is presented in R6 was used. In the FAD method, if the assessment point is inside of the diagram, it suggests that there will be no crack growth. Otherwise, the assessment point is outside of the diagram. It suggests the crack growth will occur. I will explain about the FAD method with the case of actual surface cracked pipe under the internal pressure. First, the failure assessment line, which is the criteria line for the fracture, is derived by using the tensile properties. Then the coordinate of the assessment point is calculated. The x-coordinate of the assessment point, which is called LR, is defined as applied pressure and the limit pressure. And the y-coordinate of the assessment point is, which is called KR, is defined as the ratio of stress intensity factor for the applied pressure and the fracture toughness. In here, the limit pressure PL and the stress intensity factor K could be calculated using various code, but in this study, we used API code. And by increasing the applied pressure, when the assessment point meets the FAL, the corresponding applied pressure is assumed as a crack initiation pressure. In this study, we called it as maximum allowable pressure. As a result, for the failure assessment of the cracked pipe, the tensile properties and the fracture toughness could be required. Also, in the case of hydrogen embrittled cracked pipe, the degraded tensile properties and fracture toughness is required. Usually for tensile properties, the tensile test using the smooth round bar is required. And for fracture toughness, the fracture toughness test using CT or SENT specimen could be conducted, or in our previous studies, the fracture toughness could be predicted by finite element damage analysis using the strain-based damage model. As mentioned before, for the failure assessment of the cracked pipe, the tensile properties and the fracture toughness are required. For the investigation of hydrogen embrittled materials, the experimental investigation considering the environment of practical applications such as hydrogen and low temperature should be conducted. However, due to large and complex experimental apparatus and safety concerns, it is not easy to perform many types of experiments, and it is not easy to analyze the various effects such as hydrogen concentration and temperature by using conventional experimental apparatus. Therefore, it could be efficient to predict hydrogen embrittled material properties by using hybrid approach, which is combined relatively simple tests and finite element analysis. In our previous study, the hydrogen embrittlement constant CH was introduced to simulate the behavior of hydrogen embrittled materials. The CH is defined as the ratio of the fracture strain of the hydrogen embrittled material to that of the unembrittled materials. For Fe damage analysis, the CH was multiplied to the strain damage model of unembrittled materials. This methodology using CH was validated by comparing simulated JR curves with experimental JR curves. In this study, the CH was determined using the small punch test data, which is relatively simple and useful to analyze the various effects such as hydrogen concentration and temperatures than conventional experimental apparatus. For determination of CH using small punch test data, firstly, the Fe damage analysis applying various CH was performed. Then the value which simulates the experimental maximum load was determined as the CH. And the CH for various hydrogen concentration and temperatures was determined by repeating these procedures. And this methodology was also validated by comparing simulated JR curves and experimental JR curves. In this study, the effect of temperature on the fracture of API X52 cracked pipe at low temperature was analyzed using the small punch test data and the FAD method. Firstly, to determine the strain-based damage model, the tensile test data and CNT test data was used. Then to simulate the behavior of hydrogen embrittled material, the CH was determined by using the SP test data in hydrogen and low temperature. Then to predict the fracture toughness for the hydrogen embrittled materials at low temperature, the coupled Fe hydrogen diffusion analysis and damage analysis was performed. And finally, the effect of temperature on the fracture of API X52 at low temperature was analyzed using the FAD method. I will explain more details about the coupled Fe hydrogen diffusion and damage analysis. As mentioned before, to determine the damage model, we used tensile test and fracture toughness test data. And to determine the CH, we used small punch test data in hydrogen and low temperature. The detailed procedures about determination of damage model and CH are not described in this presentation due to time constraints. And finally, to predict the fracture toughness of the hydrogen embrittled materials, the Fe hydrogen diffusion and damage analysis was performed. To predict the fracture toughness, we performed the virtual fracture toughness test simulation using Fe hydrogen diffusion analysis and damage analysis in parallel. For Fe analysis, we used Abacus program and 2D plane strain first order element with the minimum size of 0.1 millimeters were considered, and the half model considering the y-axis symmetry was considered. First, for the hydrogen diffusion analysis, the hydrogen concentration CL of the element was calculated using the heat transfer analysis methodology. And then the hydrogen embrittlement constant CH was calculated corresponding to CL and applied to the element. And finally, to simulate the behavior of hydrogen embrittled material, the FE damage analysis was performed by using the strain-based damage model and the determined CH. And as a result of virtual fracture toughness test, the left figure shows the simulated JR curves, and the right figure shows the J integral values for various temperatures. In the left figure, the black line indicates the experimental JR curves at room temperature. It shows that the simulated JR curves agree well with the experimental results. And in the right figures, the J integral values was decreased with decreasing temperature. This predicted J integral values was applied to the fracture mechanics analysis. Next, I will explain about the failure assessment of hydrogen embrittled API X52 pipe at low temperature using fracture mechanics analysis. For failure assessment of cracked pipe, the axial surface crack under the internal pressure by hydrogen gas was assumed, and as explained below. Using this crack geometry and the predicted J integral values, the maximum allowable pressure Pmax was analyzed. For determination of the failure assessment line, which is the criteria line for the fracture, the tensile tests, the stress strain curves from the tensile test was used, and the Lemberg-Osgood relations was used. It shows that the FAL for all temperatures has the same figures, so therefore we use the same FAL for all temperatures. To determine the maximum allowable pressure Pmax, firstly the assessment point was determined. First, we increased the applied pressure with fixing the crack length, and the LR corresponding the Pmax when the assessment point meets the FAL, it was determined as LR, and finally the Pmax value was calculated by multiplying LR to limit pressure PL. Right figure shows the Pmax for various temperatures. It shows that for A over T equals 0.3 with same C over A, the Pmax values for all temperature has the almost same value, and also the Pmax was decreased with increasing crack length, and Pmax was decreased with the decreasing temperature, but the differences were minor. These trends might result from the interaction effects of the low temperature hardening and ductility loss by hydrogen embrittlement. Lastly, for conclusion, firstly, structural integrity assessment for hydrogen pipelines should be performed considering the practical application environments such as hydrogen embrittlement and low temperatures. However, the large and complex apparatus and safety issues make experimenting in hydrogen at low temperature challenging. Therefore, it could be efficient to predict hydrogen embrittled material properties by hybrid approach using relatively simple tests and SB tests and finite element analysis. And finally, the failure assessment for hydrogen embrittled pipes using the fracture mechanics analysis was performed. In here, the properties degradation by hydrogen embrittlement was considered using CH, and the fracture toughness for the hydrogen embrittled material at low temperatures were predicted using the FE hydrogen diffusion analysis and damage analysis. And finally, the maximum allowable pressure Pmax was decreased with the decreasing temperature, but the differences were minor. Thank you for your attention.